Hello and welcome to the part B of the module 4. Here we are going to discuss training of the multi-layer perceptron. So in this lecture we are going to discuss the feed-forward neural network. We firstly give some notation for understanding our mathematical derivation. Then we start the training of the neural network. First the forward pass and then backward pass, which is as backpropagation. Then we give some example to understand forward pass and backward pass. Then we understand the computational complexity of the training and the space complexity of the training. So we start with the training procedure for feed-forward neural network. Okay. So as we have discussed earlier, that a feed-forward neural network have mainly three layers. First is the input layer. This layer is basically this layer, and the input layer neurons copy the input to the next layer. Okay, so this is the input layer. Next is the last layer, that is called output layer. This is the output layer, and it produces the output, and it also uses the activation function. The only difference between these hidden layers and this output layer that it produces output. Otherwise, more or less, is kind of hidden layer. And most importantly, this hidden layer that in between input layer and output layer, this is the one or multiple hidden layer. So what these hidden layers is basically do? It learns input patterns in different layers of abstraction. So what does this mean? The initial layer in general model the primitive patterns, but the later layers or deeper layers in general model the complex patterns. Now what we have to understand that what are the basic architectures of these hidden layers and how actually hidden layers is basically working and how it is being trained. Okay. So before we go further, we put some sort of understanding, some sort of notational understanding, you can say. Just for example, you said that two consecutive layer here, that this is p minus 1 layer, this is pth layer. So these are two consecutive layer, and these are the neurons. In this layer, this may be L number of neurons, and in this pth layer, it's M number of neurons. So let there is a connection from this ith neuron of the p minus 1 connection or layer to the jth neuron of the pth layer. So ith neuron of p minus 1 layer, jth neuron of the pth layer. And what is the corresponding weight? Always remember this weight is associated with this, the pth layer, because what we're going to take this input from the previous layer. So this layer. So it is weight W of P. So that superscript indicates that in which layer this weight is associated. And this from ith to jth. So ith input layer to the jth output layer or this hidden layer. So this input coming to here. So that means this. That is basically we have written that Wij denotes weights on the connection from neuron ith of the p minus 1 layer to neuron j of the pth layer. Okay. Now, similarly, in the output also, output is the last layer. So you can see there is a neuron weight. This weight is associated with this output layer. So this is the output connection from the different neurons of the last layer. So what is this O of j? So this j means now j is equal to 1 to 2 in this example. So let's say O of j. This is nonlinear function. This is a kind of activation of what? Output layer activation. And before that, we have to take the summation of Wij's, this ij's, and the corresponding multiplied with the corresponding input to this. So this is h of k of I. So this weighted sum, is fed to this output activation to get the output. So an output neuron J, denoted by O of J, is computed using a sigmoid or softmax, and where Wij is vector of weights entering the output neuron J and K, the last hidden layer which names the M neurons. So that is the way. We'll see later very details how this output is being computed. So these are just the notations what we are generally used in our examples, or some sort of. So the convention of the notation, we can say. Now the main question is that the given an input, how we compute the output. That is one of the major question in this feed-forward neural network. How actually the output being generated given the input. And another thing, that how we can get the intended output. Now one is a very important thing that to remember, that what do we mean by the training of a neural network? Because training means we have to find out such WIs, these weight parameters and bias parameter, such that given a set of input, we can get the targeted output or intended output. So that what essentially means the difference between predicted output and actual output, this difference will be very, very less or very close to zero. Okay, so those WIs and bases, how do we find? This is how do you find get these weights. So this, from a given input we can get that. This is the major question. Okay, now we coming to the training of neural network. That is essentially what basically we say, that how we get this weight and biases. So the backpropagation is the core algorithm used to train the neural networks. Okay, it efficiently computes how each weight in the network should change to reduce the prediction error. So what we have said, that we are starting from a set of weights and biases, and in every iteration we keep on updating these weights and biases, so that we can get, given an input, we can get a intended output, and whole process is called backpropagation. Okay, so when initial epochs or initial iteration, the neural network makes a prediction and it compares with the targeted answer or intended answer, and obviously you get some error. So what we have to do, we have to change the weight and biases such that this error is get reduced, and that is the basic training procedure. So what backpropagation is going to tell us, how much did we weight contribute to that error. So if we know this, that we can adjust the weights to improve the network. That means we can get a better network, so that given an input we can get more closely, or the output is more closely to the actual output. Now in backpropagation has two main phases. One is forward pass and another is backward pass, which actually called backpropagation. In forward pass, what we have seen here in a feed forward network, input flows from input to output direction. Okay, so that we also discussed that each hidden layer, a series summation of weighted inputs are done, and a nonlinear activation function is imposed on this series summation. That we have seen in our last discussion. And output of each layer is fed to the next as input. So two consecutive layer, hidden layer or input to next layer, or last hidden layer to the output layer. So this is the output of each layer fed to the next layer. And output layer, final output is produced. Then the loss is calculated. Whatever we have predicted and what is the actual, we can take the difference and we get loss. How the loss is calculated? We can use the mean square error or cost entropy, whatever is suitable. So this is done in the forward pass. We'll see in details that how actually forward pass is going to work by virtual example. And in the backward pass, these errors, what this error being calculated here, that error, we should say the error gradient flows in the backward direction from output to the input direction. So these error gradient are generated at the output level, and then in every layer from output to input, this error gradient is basically changed or kind of generated via chain rule, so that we can get the contribution of the weights of the particular hidden layer, so that we can change this to get the more accurate result. So gradients are computed using the chain rule at the different hidden layers from output to the input. So each weight gets a gradient. How changing this weight affect the loss is very important. Okay, so here we are going to understand how we compute the output in a multi-layer perceptron. That means for our a feed-forward neural network. Now here you can see that this architecture or these settings is very similar to the previous example. It is the input layers, and these are the hidden layers, k number of hidden layers, and this is the output layers. And this is the hidden layer, is the consecutive hidden layer is basically given in this way. So this is the p minus 1th layer, this is the L number of neurons in this layer, and this is the pth hidden layer. So it is a consecutive to hidden layer. Now this the weight, this wp of ij is given in this. So this weight is associated with pth layer neurons, and which pth neuron? That here you can see that this p minus 1th layer, the ith neuron of p minus 1th layer is fed to the jth neuron of this pth layer, and this, in this connection, this weight is associated. So wij, I2j, and this is p of this hidden layer. So with this setting, we try to understand how we compute the output. Now first of all, understand what do you mean by output. Output is essentially a probability, that probability of y given x. That given x, what is the probability that y occur? And based on this probability, we find that what class it belongs to. Okay. So a forward pass or iteration through the network to the find output for the given x. So in this forward pass, we try to find out that how this input are essentially through these hidden layers we get this output. To understand this, we have to follow these steps. Now here you can see that there is a k hidden layer, and input are basically go through, every input go through this hidden layer to get and ultimately we get the output here. So here for hidden layer I2 k, so all this layer we consider, and then we have to consider the consecutive layer relations, that for p minus 1 layer to p. Okay, so this is the consecutive layer. So 1 to m means 1. In this pth layer, this is m number of neurons, and is this previous layer p minus 1 layer is l number of neurons. So j is basically neural index of the pth layer, and I is basically the neuron index of the p minus 1. If we consider in this way, that we compute output all the neurons of the layer I. Okay, so the question is that what is the output of this particular. So here we can say from u0 to l, so it is 0 to l. Okay, so all these neurons are coming here. If we consider this particular neuron, So from every neurons of the previous layer it is coming, and accordingly this from which neurons it is coming, the corresponding weight. So this weight is basically this W of I, okay, because it is coming from the previous layer. And U and J, U is equal to find U to L, because which layer, which neuron is coming, and J is this neuron. Fine. So this is the basic idea to getting that what is the output of this neuron. Before we get the output, we put this activation. That what activation function is there. Okay. So now when we get this output of this layer, this output of this layer going to the as an input to the next layer. Okay. So that is, and if it is the last layer, then we get the output. So output of the last layer is the predicted output. So in this way we can get the output given the set of inputs. Okay. Now the question is that what we basically do, that this WIJP, if we can choose these weights and biases properly, that given the input we can get the intended output. The ultimate question comes here, that how we get this. But before we try to understand how we get this, let's take an example to understand this kind of the forward pass and how the output we get. Now here you can see this is the kind of very simplistic model. That is only 4 layer, input layer, 2 hidden layer, and 1 output layer. And in input layer also there is a 4 inputs. This is x1, x2, x3, x4. Input layer, it is just copies inputs to the next layer. So alpha 1 0 is just nothing but x1, alpha 2 0 is x2. This is the 0th layer kind of thing, and so on. Now what happened in the hidden layer? In hidden layer, first hidden layer, you can see here, there is 2 things. First, the summation term. So this, so it is I is equal to 1 to 4 because it's coming from the 4 input neurons, and this is Wij. Wj is basically for that this W1, and this is 1. So this is J because there is a 2 neurons. So Wji into alpha Ig. This is 0th because it's 0th, from 0th level is coming, plus bias term. So if we go for all these 4 neurons, so that we can get the summation term. When we get this summation term, we put a nonlinear activation function over it. So f of h this. So we get this output here, output of this hidden layer. Similarly, for this neuron, the same thing happened, and we get this. And again we can get this full connection. And we get now output is one thing you have only difference in hidden layer 2. It was previously from this 4 input, so that is 1 I is equal to 1 to 4, is I is equal to 1 to 2 because there is 2 input. Other things are same. They are basically series summation or weighted series summation of this. It is 1, it is 2, and rest is same, and it is a base 2, bias 2. So we get the output. So when we get this output here, okay, so this output we need to find out the output layer. So from here we get this arrow f of 0. This is the activation function of the output layer, and W3, we assume both the is W3 and alpha I of alpha 2. So that is I is equal to 0 because the 2 inputs is coming, and we get the output, and we put this activation, get the output. So this is the, it is very straightforward way to understand, or a very simplistic method to understand how this forward passes work. Given input, how we get the output, if with that 2 hidden layer. Now we are going to discuss the backward pass, which is essentially known as backpropagation. So given this feed-forward neural network, the backpropagation algorithm aims to minimize the cost function, that means the loss we incurred at the output level, by adjusting the weights and bias parameters of the network. And this weight updation is done in conjunction with an optimization method with the gradient descent. Okay. Now this error gradient, which has been derived in this here, that we get the error in this output level. So what is error? We have predicted something and there is some actual. So difference between predicted output and actual output we call error. And the error, if we differentiate this error, so the error gradient direct us how much these parameters, these WIs and biases, to change in what direction. Basically, it's one is positive or negative direction to minimize this reduction or this loss. So what is important to understand in backpropagation algorithm, we want to get the error gradient at every level in output layer in different hidden layers, and based on this error gradient we want to find out how the weights or biases and respective layers are going to be updated so that the entire loss is being reduced. Okay. So in the backpropagation, the error gradient are propagated from output to input. So in a reverse direction or backward direction, and thus the name backpropagation. Error gradient are propagated from here to output to the last hidden layer and to the next last and so on to the initial layers. Now the error gradient which is computed at the output layer directly, that is how can we get error gradient in this hidden layer or these hidden layers? We have to use chain rules that we will see later in slide. Okay, so this is the backpropagation algorithm and it's a very just overview of the backpropagation. Now here we can how the chain rule is used to find out the error gradient at different layers from output to the hidden layer to the input layer. Now you can see that E0, so that EEO means is output layer. So this E is basically error at the output level. Okay, so that's why we put E0 here. So if we E0 and this W0 is what? The weight associated in this. So this is W0. So this we get here. And now how can we get the error gradient here? That is del of E0 with respect to del of WHK, because this is the kth layer. So we use this chain rules, d of W0, d of WHK to d of E0 by W. So this will cancel out this basically. And exactly from how we get the thing of HO of K minus 1 layer, we use this chain rule. So in this way we are going or propagating from output to the input in the backward direction. And ultimately when we reach this layer 2, that this kind of chain rule we use. And in hidden layer we can get this chain rule. So this is the way that we understand, or we generate the error gradient with respect to these weight and bias parameters of each layer from output direction to the input direction. So in backward direction. And that is very important to understand. And once we get this error gradient, so it is the tth iteration, this is t plus 1 iteration. These weights, let's say it is a k minus 1 layer of t plus 1 iteration we get from the previous iteration minus this is the weight updation, that is the eta, that is called learning rate, will come later. Or also we know that from our logistic regression viewpoint what is this eta, and this is del of E0 and del of HK minus 1. So this is because this is the weight, this one there. Okay, so in this way these weights are being updated. Okay, so this is the it is backpropagation algorithm works. Using chain rule we can find the this error gradient at respective hidden layers and output. Okay, now we try to understand how actually this algorithm works. So one thing we first understand that every layer we put some nonlinearity. Let's say they use the sigmoidal nonlinearity. If this is a sigmoidal thing, this is sigmoidal. If we differentiate it, ds, then we can get this rs of 1 minus r of s. Okay. Now we use that. We assume that we have a k multilayer perceptron. We that's almost similar, but a bit slightly different notation here. That this mk is the number of neurons in this particular kth layer. Okay, so it consists of one input layer and k hidden layers. Now the ith node of the kth layer neuron is denoted by x of ik, because this is kth layer and which is the output of the ith neuron node of the kth layer. Now you can say that it is basically x of j k plus 1, this particular input. How we going to get it? That mk is the number of nodes of the kth generator, so it sum it up I to 0 to mk, w of ijk plus 1 into x of k. So we can get the output, or this basically is, we are definitely keep this sigmoidal nonlinearity over that, get the output of this, and that is going to the input to the next hidden layer. Okay. Now at the output layer, you can see that the output layer, this is the error, that is the your targeted output, and this is your actual predicted output. We take the difference, we square, and we put it to j to mk, that number of nodes here, and neurons are output layers, and normalize. Now if we take the gradient error at the output level, we find that d of e, d of ijk, this ijk is the weights the output layer. So what we get? This we get these two to cancel, so it will come, and d of xk this. Now what is this? This is basically we have to calculate. So this thing is basically d of ijk, r of j is equal to m k minus 1, so ijk into ik minus 1. So this is the basic series summation of this, and over this sigmoidal nonlinearity. And if we do this derivation or with this differentiation, after some algebraic manipulation, we get this is the value z of k 1 minus x of k xik. So if we put this value here, because this is the here, if we here, so we can get this del f del e of I jk is equal to this. We just put it here. We put this value is this, and we put it here. So this is the del of e. So this is the error gradient at the output layer. And what is the weight updation that output layer? So we can understand this is w that we have seen earlier, the t plus 1 wijk t minus this is learning rate of this. And if we put the value of this particular thing here, this thing, so we can put it here, and after this term is here. Okay. So what we can understand that this is basically the weight updation or formula at the output layer. Okay, and if we just make it a some easiness of the representation, we can put this delta j of k as this, and we put it here, the output layer. So that's the error propagated from output input layer. So this is the output layer, and this will, for every hidden layer we calculate this. So we can get the different this weight updation algorithm at the different layers, different hidden layers. So in backpropagation algorithm, what we are going to do? We initialize this this kind of parameters randomly, any random values. Then we feed the training samples, so we put the inputs. Then we do the feed forward algorithms, that how this already we have seen before by examples, the how we get these values. Then we put the back propagation. What we said that at the output layer, this del of j is this, and the hidden layer, this is bit different than this, but we can it's just some different thing than this output layer. Only difference is that we change the here by the chain rule, the error gradient change. Okay, so we get this del of ijk is basically this. So the update we wait in this way. So if for every wijt plus 1, wijt minus this. This is the training learning rate, and this for output layer, this is the del g of k, and for the hidden layers, this is the del ij. And we repeat this step to 2 to 5 until convergence. So the algorithm of this back propagation is like this. Now we are going to understand this backpropagation algorithm by using example. Now here our previous example, that is 4 layers, that is 1 input layer, 2 hidden layer and 1 output layer, and these inputs are this. So we get this 2 hidden layer to get. Now here you can see that loss, that E at output layer, E0, EO is basically int. We find in the output layer. So D is your target value, and the small d is your predicted value. We take the difference and we take square and we do this normalize. So E is your loss, EO is your loss. So we take this gradient of loss at output layer with respect to the output layer weight parameters WGO. It is DEO by DWO that we have get here. Now how we get this error gradient at the hidden layer 2? So we use the chain rule, that del of EO by d of WH2 layer 2, that we can this d of WO by d of WH2 to d of EO by d of W. So we can get this by this. So this is the gradient of loss or error gradient at hidden layer 2 with respect to this hidden layer 2 parameters, the one from the weight parameters hidden layer 2, and similarly we can get the hidden layer 1 with the hidden layer 1 parameter. We can get this, and when we can get this, we use our backpropagation algorithm, that what we have seen before. So we calculate we find the weight updation algorithm output layer as of the hidden layers, and by virtue of this algorithm we can find this. We start with any random W1, B1, W1, B2, W2, B2 and so on, and after this several iteration we find such set of parameters like Wi's and Bi's, so that we can give an input, we can get the intended output. So this loss is become very close to it, and that is the backpropagation algorithm, the agenda of that. Okay. Now what is the computational complexity is associated with this? Now it basically is very much proportional to the number of trainable weights, including maths. So the complexity of backpropagation depends primarily dominated on the number of matrix multiplication, and which is basically on this W, how many trainable weights are there. So it is exponent big O of W. Now we can say that total number of parameters is W, number of layers L, and the number of neurons in the layer is NL. So this W is this. So computational complexity in forward pass is big O. And in backpropagation also, in this pass backpropagation consider the gradients with respect to the weights, gradient with respect to the activation, both in order of this W. So both in W. So total computational complexity of training part sample is big O of W. and if there's a batch size, so b number of samples, so it is b. So this is the complexity or computational complexity of backpropagation. There is some space is also required for this. So what is the space complexity of this? That during the forward backward path, the algorithm requires the storing that the intermediate activation and error terms for each of the layer. So the space complexity is also denoted by depends on this number of weights. W is the total number of weight parameters, weight and biases. So it is also big of tau. Now this is the storing the intermediate activation. So during backpropagation, as we said that for efficient gradient computation for chain rule, output activation for each layer during this forward must be cached in saved in the memory, and that's why this space is required. And this memory commits grows linearly with number of layers and number of neurons per layer, so total number of weights and biases. And there is some auxiliary space of gradients is also required to store the gradients for each parameter. Some extra spaces may be required, which the same dimension of the parameter themselves. So this is ultimately boiled down to this big of W, where W is the total number of weights and biases. Now there is another thing. There is some improvement can be done on this, or you can say some optimization can be possible. That's called checkpointing. So in standard implementation, we can say if n is the number of is basically space complexity of n is n. Okay. Now this checkpointing or judicious decomputation can be used some trade-off between the time and space. So what is going to, we can say here that standard approach is big of n. So you can say this n or w is the kind. Says compute all, store all the activation in the forward pass. This is time efficient but memory intensive. Okay, so this is between the time and we can say normal this. That's why. Now one thing we can do with recomputation approach that the space complexity becomes almost constant, but we need the n squared time. So what we done in this case, we recompute the necessary activation during backward pass as we did, and this significantly reduces the memory usage because it's becoming constant relative to the number of layers, but increase the computation time. So the checkpointing is basically a judicious selection between these two extreme cases. So this method is somewhat in between, where they involve the storing only a selection of activation and recomputing others, allowing for a balance between space and time complexity anywhere between big O1 and space. So this is the some sort of optimization in the space complexity. Okay. So in summary, so in this lecture we introduce feed-forward neural network, give some notation, and then we can the training of the neural network, forward pass and backward pass, and as a backpropagation. Then we start the training of a neural network and forward pass and the backpropagation. An example has been given. Then we see the computational complexity of the training and the space complexity. Okay. In the next lecture, we are going to introduce the deep neural network. Thank you.